introduce all of you Professor John Warren Harvey. Jack Harvey doesn't need much of an introduction for many of us. Jack has been collaborating with the magnetic field group here at IC, but also with the helioseismology group. Jack has been doing instrumentation in magnetograph, like similar things what we do. He's been the PI and the designer of GONG. GONG is here at Teide, together with other 6 stations around the world. I was this morning looking at Jack's curriculum, and it's just impressive, as you can imagine. Jack, the number of papers or citations is just enormous. I mean, I don't need to give the numbers. It's very, very large. But one of the things that is interesting is that, or surprised me, is that your PhD that was defended at the University of Colorado, Arecibo, at that time in 1979, it almost suggests everything we've been doing here in solar physics. Everything is suggested there, and it has every year, even last year, between 4 and 6 refereed citations. Since 1979, this has always gotten citations every year in the number of 4, 5, 6. So I think this is spectacular, that a PhD defended that long is still so interesting today. The topics that where the thesis is cited is, I have the list here, is something like time distance, helioseismology was suggested there, internal rotation of the sun, this is related to the GONG work he did, magnetic flux tubes with FTS, they found the kilogauss fields together with Jan Stenflo using FTS data, the active region prominences, that was the main topic of the PhD. Scattering polarization is suggested there. Heliospheric magnetic fields, it does have an influence with the work he's been doing. And the polar fields that are also popular these days, they were already studied in his PhD. And even 1.5 micron polarimetry is suggested there. Your paper in 1973, Harvey and Harvey on moving magnetic features, is the paper that I read more times during my PhD. So for me, it's really a reference and a pleasure to introduce Jack Harvey. Jack moved then to the National Solar Observatory. He's in Tucson, Arizona, where he's now working with SOLIS. SOLIS is an instrument, it's the new generation of vector magnetic fields that they are doing in Tucson. They want to bring one of the SOLIS instruments here. It's something that we will be having visitors in 1 month from now to see if we can get one of the SOLIS instruments here. And I think Jack will be telling us about the new advances of mysteries of the magnetic sun, including new data from SOLIS. So Jack, please.
Buenos dias, mis amigos. I wish I could speak in Spanish to you, the beautiful language, but I can't. I'm just an ignorant American. I hope that in the next hour you will find something interesting that we can all enjoy. I've had a long career, as Valentin has very kindly reviewed. I didn't know that my thesis was still being referred to. There are a lot of mistakes in it. But my degree hasn't been revoked yet, and I guess it won't be. So this is going to be, I hope, an interesting and fun exploration of a few of the mysteries of the magnetic field in the sun. It's always intrigued me since I was a teenager, and there are many mysteries of the sun, and some of them have been solved, some of them haven't, and we'll look at a few of them. And so let's get started here. I wanted to give a framework. We, nowadays in solar physics, a lot of us are involved in space projects and increasingly high-resolution campaign observations to try to find the small details, the fine structure of magnetic fields on the sun. They are interpreted with sophisticated inversion codes that synthesize the spectrum lines that are observed, and much of that work is originated here, and this is probably the home of sophisticated inversion codes. And the results are wonderful, but I'm not going to talk about that because there are experts in the audience who could say better things than I can. So I'm going to talk today about the other end of the range, moderate resolution, ground-based, and long time periods, observations that are made for decades. The 3 topics I wanted to look at were magnetic field changes with solar flares, magnetic fields in the quiet sun, and magnetic fields in the chromosphere. And in each of these topics, as time permits, I will give a little bit of history, what the mystery is about these issues, and some new results. And if I launch into too much jargon for you, please say, what does that? And if you get bored with it, if you leave, that's okay with me. Well, here's a brief history of the magnetic sun. And I was fascinated some years ago to read in Kepler's book, which was the big popular astronomy book of its day, that he suggested the sun was magnetized. This is before the discovery of sunspots. The reason he needed to call on a magnetic field was to keep the planets moving in their orbits. Remember, in 1600, Gilbert had just made a big treatise on the Earth's magnetic field, so it was a hot topic in physics of those days. And so Kepler borrowed that idea and said, well, you need to have something to move the planets in their orbits. Why not a magnetic sun? So the idea was wrong, but the basic notion is correct. And then there's a whole range of people, pictures of these guys, and one thing I've noticed is that if you have a mustache, it seems to be a good thing for making a point in magnetic fields. So Javier, you're all going to have pictures in the future. So there's a long history of magnetic studies of the sun. Really, it started about over 100 years ago. Of course, with the discovery of the Zeeman effect, which is what we use to make the measurements for the most part. And George Hale here observed the Zeeman effect in sunspots over 100 years ago now. And systematic observations have been made ever since. So these are some of the highlights. Now I'm going to turn to the subject of magnetic fields and solar flares, something that's interested me since I was a young person doing a flare patrol during the IGY, of all things, a long time ago. Well, solar flares are an interesting problem for astrophysics. They are the most powerful explosions in space out to a couple of light years at least. And it's an enduring problem in astrophysics ever since the first one was observed in 1859. Now, people have wondered about what might cause the solar flares, and the considerations of energy and the location of the flares makes it obvious that they have to have some sort of electromagnetic origin. So people looked for that. And there are many models of flares, but in essence, most of them are that the flare is a result of a sudden release of energy to an MHD catastrophe, and mainly the process involved is field line reconnection and a multitude of events that follow that initial field line reconnection and release of energy. So for many years, during my career in particular, people were focusing on the post-flare phenomena because they're spectacular and visible. We still haven't actually seen the seed of the flare, so that remains to be done. Here I'm going to try to show you a movie of one flare. The flare occurs here. These are movies made from the ground in the H-alpha line, and they're just looping around. See, the flare occurs there, and a wave shoots out. That's a so-called Morton wave. They're not all that uncommon. It shows the range of the disturbance that a flare produces in the solar atmosphere. If you look at this dark filament here, this cloud of cool gas hanging in the solar atmosphere, notice when the blast wave goes by, it jiggles the entire prominence out of the passband of the filter. So that's a typical, well, not a typical flare, but a bigger flare. Now, what's the mystery? Well, Ron Giovanelli here was the first to say, there must be a magnetic field change when a flare occurs. So he looked, but the data in those days wasn't very good, and so he didn't have a conclusive result by any means. I should also note that in 1946 he originated the key idea of magnetic field line reconnection, which is very important in many astrophysics applications. Then in the 1950s to the 1990s, people built various magnetographs for making maps of the magnetic field in the sun. And Ron was one of my mentors, and Bill Livingston here is another one of my mentors. And he was responsible for a number of very important magnetograph developments. And I've been happy to work with him for the last 50 years, I think. And he's still observing at age 84. And so solar people just never quit. But the magnetographs in the 50s to 90s gave results that were very contradictory. Sometimes you saw field changes with flares, sometimes not. So that's the mystery, what's going on. Why were these earlier observations not so good? Well, they had poor sensitivity, low spatial resolution. Remember, when I started in the field, we didn't have computers at Instrument. Everything was done photographically or with strip chart recorders. So it had bad sensitivity, low spatial resolution. The observations weren't made very frequently, and we had terrible time coverage of flare events. Furthermore, it turns out that when a flare occurs, the photospheric lines that are used for magnetic field measurements go into emission briefly at the time of flare. There's a lot of heating going on, and that produced transient effects that looked like magnetic field changes but really weren't. So that confused the issue. Well, moving toward a solution, in 1999, high-cadence observations became available. They were done on a routine basis, mainly at the Big Bear Observatory. And they began to show a consistent picture of real permanent magnetic field changes at the time of a flare. But those observations weren't conclusive either, because other observations were being made elsewhere, still giving inconclusive and contradictory results. In 2001, the GONG network that Valentin mentioned had an upgrade in resolution. And I should say that the GONG telescopes have an aperture about the same as Galileo's telescope. So it's not much of a telescope. It's very expensive, though. And we started to produce full disk magnetograms, that is, measurements of the line of sight component of the field, once every minute with a daily duty cycle, about 85 to 90% around the world every day. This is one of the magnetograms, a map of the line of sight component of the magnetic field, in which gray or dark is one polarity of the field, say inward, and white is outward, and gray is zero. So we see a sunspot region and bipolar nature, positive and negative. Again, our telescope aperture is 2.8 centimeters, not very big by today's standards. 2.5 arc-second pixels, 1 minute exposure, and so on and so forth, about a 3 Gauss noise level. This is an observation made in November of 2000. And I'm going to look at this region here in a little more detail. There's that region again, up along here, every 5 minutes in magnetic fields, showing plus or minus 1,000 Gauss in the range. And much does indicate when a flare started and when it reached its maximum intensity. So there's not much going on there. But if we take an image at the beginning and make differences of that as a function of time, we see changes. That was a pretty good indication that there really was something going on that might be reliably studied. Less than half a year later, another region flared like that near the limb. The limb of the sun is about here. Here's the average magnetic field over about a half an hour. And we subtracted that image from all the other ones. And again, big changes when the flare occurred. So a colleague of mine, Jeff Sudol, and I looked at this in more detail. And we remapped the images of the magnetic field. And every box here represents 1 pixel in the map of the magnetic field. And it also represents 4 hours of time and about 500 Gauss of magnetic field. And what we see here is the magnetic field before the flare, pretty steady. Then there's an abrupt change to a new level. And that's a pretty consistent picture over the area covered by these pixels. However, down here, we see something a little more nasty. A changing field at the beginning, before the flare, and then a big transient. This is the spectral line going into emission that I mentioned earlier. That disturbs analyses that we make of each one of these pixels. But one can fit a function of a certain type to each one of these time series and deduce from it what the magnetic field is doing as a function of time. Here's an example of some of that modeling. Let's look at this one. Here's the magnetic field as a function of time. The 3 bars represent the start, maximum, and end of the flare. And we fit a certain function to the data and can get results like this. We get the parameters from fitting that, get the mean field, which doesn't change over the period of observation, This is a linear component of the field change. This is the one that we're really interested in, the sudden change, the sudden abrupt change of the magnetic field. And then there are some other maps which I won't take time to explain in detail. But one of the things we've been interested in, because these observations were so hard to make for so many years, is how large is the field strength change? Mind you, again, we're only looking at the line of sight component of a three-dimensional field. So in our earlier study, we looked at 15 X-class flares. Those are very strong ones, strong X-ray emission, the most powerful flares that we see. And we found that field changes were of the order of 100 Gauss. That's not a small change to today's instruments. In earlier instruments, it was hard to observe things like that. Now in a new study that hasn't been published yet, we've looked at 38X and 39M flares, M flares being less strong than the X ones. And we have a new histogram, again showing that 100 Gauss field changes are not unusual, but including these weaker M flares, the amount of magnetic field change is somewhat less than 100 Gauss typically. Yes? At 1 pixel, yeah. This is essentially a synopsis of the results of various active regions, many active regions, 38X and 39M active regions. And we've selected particular pixels, so there's substantial selection effect in this. But there's only one representative measurement per active region here. Now, another thing that is interesting is how fast does the field change? Is it instantaneous? Does it take minutes, hours? Well, fitting the changes with the function that I indicated earlier, again with our earlier study with 15X flares, the change was pretty fast. Half of them occurred in a minute or so. And then there was a long tail of longer duration field changes. Now, including the weaker flares, we see that the histogram, or the cumulative histogram, is not so peaked at very fast changes. Changes are a little slower, on the order of 10, 15 minutes, typically. So the powerful flares change the field rapidly. The weaker flares change it less rapidly. Now, the really interesting question was, when does the field change? For example, if it changed before the flare, you say, aha, we've got the cause of solar flares, something that's been looked for many, many decades. Well, it didn't turn out to be the case. In the earlier study, we found that the change was almost always after the flare. In fact, there were just a couple of noisy points here that I didn't plot that stuck out a little bit before the flare, but there was noise. So typically it was about 10 minutes after the flare. Now when we add many more flares and weaker ones, the histogram has come a little bit closer to zero, and in fact there are some flares that seem to have their field change before the occurrence of the flare. But this turns out to be an artifact of noise, and those of you who are really interested can see in the paper that after correcting for the slower and noisier, weaker flares, it's consistent that the changes are after the start of the flare. So the field line change, magnetic field change in flares, is a consequence of the flare, not its driver. A few more properties to wind this section up. Nearly every flare we've looked at with a classification of M of 5 or greater show changes. And we just have not enough sensitivity or coverage to look at the weaker flares. I suspect with more sensitivity, even weaker flares would also show changes. The amount of the flux change is pretty large. 10 to the 21 Maxwells is a substantial amount of flux comparable to what's in active regions. The changes are largest near the limb. Again, we're looking only at the line of sight component, not the whole vector field. So that suggests that the horizontal component is what's changing most significantly. Changes near the disk center decrease the field in the ratio of 2 to 1. Twice as many of the changes are decreases than increases. And near the limb, it's about equal. Sometimes we see increases, sometimes decreases. The changes tend to be associated with the penumbra of sunspots. And as a function of time, the change can be watched as it propagates across the active region. It propagates like like flare emission observed in lines like H alpha. So the prospect for this topic is that we have to get after the theoreticians. Theoreticians love to make models that explain almost everything, but not everything. And most of them have left out the fact that there are magnetic field changes in the photosphere. And that was unpleasant, but I got after some of my theoretician friends, and they're beginning to look more carefully at this. And Hugh Hudson in particular has come up with a model that possibly explains what's going on. The observational scenario, though, is still not completely clear. Some of the results, many of the results are consistent with the idea that we have a penumbral magnetic field that's mainly horizontal, and as a result of the flare occurring up in the corona, there's a reconnection event, and some of the field lines start shrinking. That pulls the penumbral field up. Consistent with that is the disappearance of the penumbra associated with some flares. So you imagine the field lines are going like that. That's fine. A lot of the observations are consistent with that. But we also observe polarity reversals, and that isn't consistent with just pulling the field lines up. So there's more to the story than that. We really need the vector observations, and as solar activity begins to increase with the new solar cycle, we're going to be making those. And observations from the new SDO satellite will no doubt make that a lot clearer. Now I'm going to turn to a subject which is very popular around here, the quiet sun magnetic field. I'm a little reluctant to talk about it here because there are people in the audience who know more about it than I do. So I'm going to concentrate on some of the earlier observations and some new stuff at the end. What's the mystery? Well, Hale was able to observe magnetic fields in sunspots in 1908, and he immediately got the notion that there must be magnetic fields elsewhere on the sun and started looking for them. He built this tower, which is something like 40 meters high. I spent a few summers at that place. It was an interesting experience for a young guy. There's a person climbing up the ladder there. That wasn't me. So anyway, Hale, shortly after he discovered magnetic fields in sunspots, was searching for the general magnetic field of the sun. And it wasn't a very successful search. The observers, mind you, all these measurements are done visually with looking at the spectrum line to see if it's split or not by the Zeeman effect. Sometimes the observers would see the splitting with no sunspot. And they called them invisible sunspots, which doesn't make much sense, but that's typical of a lot of astronomical nomenclature. The search was unsuccessful, though, until the Babcocks built the first mapping magnetograph in 1952. That made maps of the whole disk of the sun and revealed that there were magnetic fields all over. This is not one of those 1952 observations. This is one we made at Kitt Peak long ago with an instrument that no longer exists. But it's kind of pretty. It shows the magnetic field of the sun, and I've blown up part of it for you to see here. Again, we have the active regions, and out in the quiet areas of the sun, we have these little dark and white features. These are the network elements. Convection flows in the photosphere tend to concentrate magnetic fields into stronger features, and they show up in a mesh pattern that's called a network. You can see it perhaps a little better here. Cellular structures about 20,000 or 30,000 kilometers on the side. Now we're going to turn up the gain a little bit and see what else we might see. So here we've cranked the gain up about a factor of 5 or so. And now we begin to see that there's structure inside the network features. And some of that is just noise in the instrument, but other of it is real magnetic fields there that are just weak. And observations like this and other ones showed that there are magnetic fields in most of the quiet sun. So we went back and looked at earlier observations. Why didn't we notice that before? Well, one tends to be a little blind sometimes when you're looking for one feature and you ignore something else that's right in front of you, and that happened in this case. Here in 1964, Bill Livingston made a high resolution for those days observation, And sure enough, here's a network feature that I've outlined, but there's mixed polarity features inside the network. 1970, a new instrument came along. We see the same sort of thing, little specks of magnetic field around in the quiet areas. Another instrument came along in 1973, and in 74 we got some observations with it. Here in the photosphere, we see a network cell, and inside it there are these inner network fields, as we call them then. Nowadays it's called the inter-network. In the chromosphere, though, same time, hardly any sign of it. Most of this structure is just noise in the instrument. So we had the notion that maybe the inner network fields were confined mainly to the photosphere. Before 2006, there were a lot of things known about these features, again, mostly with line-of-sight observations, just the line-of-sight component. They're compact features with pretty small fluxes, a few Gauss over a few arc seconds, lifetimes of hours, mixed polarities. They tended to flow with the supergranular flows, the convection flows. There was very scant information about any component other than the vertical component. They were usually observed at this center. There was really no notion of what the field strength was, and they didn't seem to appear very strongly at all in the chromosphere. But now we now know that there is a horizontal component as well as a vertical component of the inner network field. And it turns out that that discovery was kind of missed too, missed opportunity, but there were sure good hints of it. Again, back in 1970, this is an observation of the line-of-sight component, but it's near the pole, so we're sensitive to horizontal components of the field. There was a mixture of opposite polarity fields here, besides the strong unipolar fields that one sees near the solar poles. This is just noise for comparison. Bruce Leitz in 1995 was making observations of the transverse Zeeman effect, which is sensitive to the horizontal component of the field, and he detected small glitches in the spectrum line indicating the appearance of strong, transient, horizontally oriented magnetic fields. So 95 revealed that. 1996, a group of people at Kitt Peak made observations that also supported the notion that weak fields got stronger as you got near the limb, whereas the vertically oriented components, prominent near this center, became hard to see near the limb. There were other people who contributed to that era of knowledge, Sarah Martin in particular. So we had these hints before 2006. There were weak fields everywhere on the disk, lifetimes maybe 10 minutes now, not hours. Mixed orientations, that is, the field line orientation seemed to be any polarity. Bruce Leitz had found that there were these strong horizontal fields that occasionally appeared, but they're pretty rare. The relative fluxes of vertical and horizontal components were very uncertain, and the significance and ubiquity of the weak magnetic fields in the quiet sun were just not fully appreciated. Now I'm going to show, this is a movie in a moment. It's a GONG magnetogram of the same flare event that I showed you earlier. Now this is in magnetic fields. I made this movie because I wanted to see if that flare wave would show up in the magnetic field. And it turns out it does, but it's extremely weak, and I haven't really pursued that. So I made this movie, and let's see if we can get it to go. There we go. Now, the GONG instrument was not designed to measure magnetic fields, so it doesn't do a real good job of it. That's why there's a lot of noise and wiggling here. But I've taken out solar rotation. This is a period of about 7 hours. And as I was looking near the limb here for this flare wave, I noticed that, gee, near the center of the disk, you see the network fields nicely and a few inner network structures just at the limit of visibility. But it's pretty quiet. Whereas near the limb, there's this seething action, a lot of changes. Let's take a closer look at that. This is a blow-up now of the disk center and near the limb. You see it's relatively quiet near the disk center. But near the limb, if you focus on any feature, see that it changes pretty rapidly in time, except for the long-lived network features. Furthermore, as you get closer to the limb, it seems like that rapidly changing fraction is larger. So the implication was that there was a horizontal component of the magnetic field that changed rapidly. So we studied that a little more in detail by taking the 7 hours of magnetograms, making an RMS of the magnetic field at each pixel, and then making a map of it. And that's what this is. Dark means there's a very small change over time of the magnetic field, and light means there's a relatively larger change over time. So we're displaying, however, here a very small range of magnetic field change in the RMS. But the point is that the variance in the magnetic field measurements increases as you move from this center to the limb. And it was a linear increase. Linear implies it's mostly a horizontal component that's doing that. So quantitatively, we can plot that RMS as a function of radius from the disk center here. So that's the observed curve, very nice and linear, except right at the limb where noise from atmospheric turbulence and so forth adds a lot of signal, which is not solar. We have to correct for the noise in the observations. The noise model is here. That's based on limb darkening and how many photons are collected and so forth. After doing that noise correction, you get this curve. And that's fit by a model in which the horizontal component of the magnetic field isn't perfectly horizontal, but is inclined at about 74 degrees. So what we conclude from this is that the quiet sun has a strong, relatively ubiquitous, and probably strong, because these are very low resolution observations, horizontal component that changes rapidly. Well, you wonder what it might look like in the chromosphere, higher up in the atmosphere. These are not our best observations. I'd be happy to show you better ones. I just couldn't get them into the presentation. I can show those to anybody who's interested privately. These are magnetograms made in the calcium 8542 line up in the chromosphere. And again, this center here, limb here, you don't see the same effect. There's not much change going on in here, say, and there's not much of that seizing action going on near the limb either. So the preliminary conclusion, now supported by later observations, is that this horizontal component, rapidly changing component, is not so present in the chromosphere. And that's very surprising, because in almost every other kind of observation of the chromosphere, you see nothing but action, very dynamic. There was confirmation of the existence of these horizontal components from observations with the Hinode satellite. Here's the vertical component at this center and the horizontal component. The observations take a long time to make, so there was no information about how rapidly these features are changing, at least in these earlier observations. Modelers, in this case, were ahead of the observations. Here's just a sampling of some of the results of modelers. Let's look at this one, which I think is especially nice, by Bill Abbott. It's a kind of a perspective view of the photosphere. You see the granules here. It's a real blow-up. Nothing like the resolution we had in the observations, but the field line maps show that there's a lot of horizontal tracing of the field lines, as well as, of course, the vertical components that are more permanent. So he already had that, as did other modelers. So the existence and properties of the horizontal field are pretty well known to the modeling community. Now here's a new result. It's a little hard to explain, so I'll try to be brief on this. This is a 2006 to 2010, and each one of these little strips here is essentially a chunk of the sun along the central meridian, in which we've compressed it to 1 pixel wide. But the signal in there is the net magnetic field. So up at the North Pole, we have the polar magnetic field here as negative. The South Pole of the field is positive. And in between, we have the existence of active regions, which come and go you can see the 1 month or one solar rotation period. The question was, what's happening in the background here in the quiet sun? The lower plot is essentially the same thing, but instead of averaging the net signal, we're averaging the total magnetic flux in the area of the sun that's being examined. And here the question was, does that quiet sun magnetic field change over many rotations, or 4 years in this case? And the preliminary look at this is no. That inner network field seems to be not changing over this 4-year period. You have to look at it in a little more detail, but that seems to be a pretty solid result. We can go back using earlier observations into the 70s, and that's what we're planning to do. Now, regarding the horizontal magnetic field, it is ubiquitous. It seems to be everywhere. It seems to show no latitude or longitude variation. It's extremely uniform. And again, the embarrassing thing, it was observed. We saw it easily in earlier observations, but never appreciated it. It doesn't seem to be very strong in the chromosphere. It's probably the result of old magnetic flux being shredded up, torn, and recycled by the granulation as part of the local dynamo, and occasionally eruption of new flux. The rapid time variations indicate that the granulation is driving all of this rapid change. But power spectrum analysis showed no 5-minute oscillation, which one would expect from something driven by the granules, which have such a strong 5-minute period associated with them. And as people who do this work here know, there's a lot more to be done. Now, in my last section, I'd like to turn to the chromosphere. When I was a student in university, I did a paper as a class project on chromospheric magnetic fields, and I'm still studying them. What's the mystery? Well, the chromosphere is an interesting place, lots of dynamics, lots of challenging physics. It's a transition from dominance by hydrodynamic processes down below in the photosphere to magnetic field dominance in the chromosphere itself. And there's strong gradients in temperature, density, magnetic field. Radiative transfer is complicated to everyone except Harvey, and it's very dynamic. There are waves, shocks, explosions, everything going on there. So it's fun to look at, but hard to understand. Around 1980, we knew a little bit about it. The fine structure of chromospheric features follows the magnetic field lines. The umbral magnetic fields, which could be measured with early observations, weakened as you go upward, as you might expect, as the field lines spread out. The active region magnetic fields were in the chromosphere fuzzier and weaker than what you see in the photosphere. There's something called the canopy effect, which around here, I think the analogy is a palm tree. We have a strong vertical component of a magnetic field, and then as you reach the photosphere and chromosphere, it fans out, causing what has been called a canopy. And that canopy effect is easily seen in the chromospheric observations, implies that the field is rapidly spreading with height, and that there are components that are horizontal in the chromosphere. Prominences, these clouds of cool gas hanging in the corona, had magnetic fields on the order of 10 Gauss. They tended to be horizontal and sheared, and occasionally there'd be active prominences with loops and other dynamic features, and the field strengths would be up to 200 Gauss. But that was about all that was known. Chromospheric magnetic fields are hard to measure. I've spent my career doing it from time to time. There aren't very many spectrum lines. We use the 8542 calcium line. The spectrum line shapes changes a lot in ways that are not related to the magnetic field at all. You've got to allow for that. The polarization is not produced just by the Zeeman effect. You have to allow for that. The signals are weak because the lines tend to be broad and deep. So it doesn't make for much of a polarization signal. And one should use a state-of-the-art inversion code, such as Hector has developed, for analyzing these observations. But we're not there yet, at least not for every day, and not by me. And what I'm going to present now as a wrap-up is, can we learn anything by ignoring all of this stuff? Well, we can maybe fool ourselves, but let's have a look. With the SOLAS instrument at Kitt Peak, we make daily measurements of the 8542 line for polarization, Doppler shift, line strength, and here line intensity, core intensity, and ignore the egg-shaped appearance of the sun. That's a technical detail here. This is what the core of the spectrum line looks like if we make a map of the distribution of brightness on the sun. So we have the active regions as plages, and here's a filament, a cool gas hanging in the corona. Now, if we take that observation, instead of looking just at the core intensities, we look at the magnetic field strength line of sight component out in the wings of the line, which are formed low in the atmosphere, more or less a photospheric measurement. We get the typical magnetogram showing network features and not much else, plages. And it looks like a typical magnetogram that we're used to looking at. And now if we measure the polarization in the core of the line, where it's formed up higher in the atmosphere, we begin to see the same features, but it's a little bit fuzzier, and we're beginning to see diffuse areas in it. To show that better, let's turn up the gain now. That's that same core magnetogram, line of sight component. And we're beginning to see diffuse features in a lot of places. This is the pole up here. Now, if we take the difference between the core magnetogram and the wing magnetogram, we see a few things. First of all, a lot of instrumental noise that we haven't fixed yet. But aside from that, we see that there's features near the disk center that persist. This shows that at the disk center, the chromospheric magnetic field strength is less than the photosphere. That's what the dark sign means. Whereas near the limb, it's the reverse. And there's a zone where the field strengths are about equal in this subtraction. The chromospheric fields are stronger, or appear to be stronger, near the limb than the photospheric ones. And then there are these diffuse features. Here's a big diffuse area. Here, here, here. What's that all about? Here's a close-up of the disk center. I won't repeat what I just said. And again, near the limb. Looking at those diffuse fields, here's one rotation, or partial rotation of the sun over a few days. And I've outlined an area which you see is pretty white in there. This is the line of sight component of the field. As it moves across the disk, approaching the central meridian, you get some dark features, and the whiteness is not as strong. And over here, on the other limb, it's very dark. So this is pretty good evidence that the horizontal component of the field that we're looking at here is pointing toward us on this side and away from us on that side. These diffuse patterns persist over several rotations. I won't go into that. But turning again to this, you get the notion that you ought to be able to use the passage of the feature across the disk as a function of time to reconstruct what the field components are, if you make the assumption that the field hasn't changed in time. And for these diffuse features, it seems like they don't change very rapidly in time. So we do that using a so-called synoptic chart, which we take full disk images of the sun and map them into a map of the entire surface of the sun, like a weather map of the whole globe of the Earth. But instead of using just plain magnetograms, we can decompose those observations into two components. Basically, one that is sinusoidal with respect to the central meridian, and one that is cosine with respect to the central meridian. So we don't just use the observed field along the central meridian as typical with synoptic maps, but we use the whole passage of the field across the disk to express the field in a zonal component, that is an east-west component, and a meridional component, which we can't distinguish whether a north-south component or just a radial component. We don't have enough geometry change across the passage of the region across the disk. This is not too easy to do. You have to account for differential rotation and other technical details I won't go into. And again, it only works on large-scale stable features. And I did a test case motivated by giving this talk. And here are the results. So these are new results. Here's a typical synoptic map showing the meridional component of the field, that is the north-south or radial. And it looks almost exactly like an old classical magnetogram synoptic map, which you just see mainly the vertical component of the field. And the same thing in the chromosphere here. They look about the same. Now here's the east-west component. Doesn't show much of anything except noise due to the evolution of features. We violated the assumptions. But in the chromosphere, there are east-west components that are not seen in the photosphere. And these are kind of interesting. Here I've taken the difference between the chromosphere and the photosphere. This is still the same. And this is the meridional component, which now is beginning to show something, the north-south or east-west, north-south or radial components. There's something interesting there. But the east-west difference is really interesting now. There's diffuse structures in many places. There are features on the sun in the corona called coronal holes. That's where the magnetic field is open to interplanetary space. And observations like this one in the ultraviolet, the coronal holes show up as dark regions where there's not much emission because the material is essentially not trapped there to emit and escapes to interplanetary space. Excuse me. So the idea is, what does this coronal hole look like in these maps? In the photosphere, it's been known for decades, since the 70s, that the coronal holes are associated with unipolar regions. That is where the magnetic field is almost always coming up, say, or going down in this case, unipolar, at least on the large scale. In the chromosphere minus the photosphere, well, again, in the meridional component, not much. They're about the same. But here, much to my surprise, there was a lot of structure in the east-west component of the chromospheric field in the coronal hole. Well, how can that be? The field is open. It's supposed to be pointing up to space. Evidently, there are tilts to the field that change across the coronal hole, giving these light areas and dark areas. This is only one case. We'll have to do a lot more. But it looks like there's a lot of fine structure in the chromospheric orientation, chromospheric field orientation in coronal holes. And then there's this little feature. Let's look at that. I've mentioned filaments several times earlier, these clouds of cool gas that hang in the corona. In this H-alpha image from the Big Bear Observatory, there's the full disk and a close-up. I've tried to outline with the mouse, not very well, as you can see, a trace of that filament. And then I've reconstructed disk images corresponding to about this time from the synoptic maps of the east-west and meridional components. And let's look at this one first. It's been known almost since the first day of the magnetograph that the filaments trace an area that is between opposite polarities. There's positive polarity on that side, negative polarity on that side. There's nothing new there at all. But in the east-west component, there we have some interesting things. The prominence or filament follows along a dark path in the chromospheric magnetic field. This supports one of the major models of how prominences exist and are formed. The so-called Kuperus-Radu model is very consistent with what's observed here. The other model that is even more vintage, Kiepenhahn-Schluter model, imagines that we have field lines coming up from the opposite polarities, and there's a sort of a hammock that forms in the field lines, and the prominence hangs in that hammock. That's not consistent with this picture. That doesn't mean that all prominences are following the Kuperus-Radu model, but at least this one is much more consistent with that idea than the Kiepenhahn-Schluter model. We'll have to do a lot more of this with other filaments and see how ubiquitous this result is. So on the chromospheric field, the prospects, I think, are just terrific. There's a lot more to be learned. It's a very complicated region of the sun's atmosphere. It's been researched for over 100 years. Hale looked at the chromospheric magnetic field in his first observation. This is definitely not an easy research area. You have to be bold, and even more of an optimist than most of us are as scientists to tackle this one. Need the full Stokes polarimetry, no question about that, and a very careful analysis using the kinds of advanced inversion codes that have been developed here. Large areas of the chromosphere are dominated by mainly horizontal field with properties that are different than other areas of the sun. They're not like plausias, they're not like sunspots, they're not like filaments. They deserve much more study. I'd say that rewarding times lay ahead for anybody who wants to tackle an interesting problem in the chromospheric magnetic fields. Let me wind up, first of all, by thanking the people who invited me here. Some years ago, I was on a committee that reviewed the scientific program of IAC, and we recommended that the programs be strengthened here. Never once believing that I'd ever be a beneficiary of it. It seems a little self-serving, but anyway, I'm glad to be a beneficiary of it. And I thank the people who have done such a marvelous hosting job. But let me wind up as far as the magnetic field is concerned. In my long 50-year plus career, a lot of the magnetic field mysteries have been solved, and that's wonderful to see. But it's also wonderful to see that there are many more mysteries. And in my view, and I live in an area that has a nighttime observatory, Kit Peak, so I see a lot of interesting astrophysical problems. I'd say the mysteries of the sun are just as challenging as any in astrophysics. Just to give a few examples, there are many, many of them. Always been puzzling to me, where does the magnetic flux go? We see it pop up, but it's not so easy to see where it goes. And that's still a big mystery in my view. How does the solar cycle work in detail? Got a rough idea, which may or may not be right. And it seems to explain some of the things, but the details are definitely not known. Near the poles of the sun, there are mass flows, meridional flows. And we don't know in detail exactly how they work. They seem to be perhaps important in the solar cycle, and we need better observations of them. Finally, stars are not very important in the cosmology of the universe these days. Baryonic matter, 5%. Stars, some fraction of that. Our star, not very significant as stars go. But it's our star, and we need to know more about it. And we depend on it. We need to know more about it. So there are exciting times ahead for anybody who studies our star. Thank you very much.
Thank you, Jack. It's time for questions. Yeah.
Okay. First, thanks for this beautiful talk. Okay. I have a few questions, but I'm not sure that I'm okay. So let me start with the first one, and have to do with the modification of the magnetic field, the changes of the magnetic field associated with the flares that you have presented. In textbook, you find that the magnetic fields that you have in the corona are sort of driven by the topology of the magnetic field that you have photospheric levels, are dictated by the fields that you have down there. So it's hard to understand how, by modifying the magnetic field that you have in the corona, you modify the photospheric magnetic fields, because it goes the other way around. So how this can be? Could you comment a bit on?
Sure. Yeah. To state your problem a little more colloquially, it's like the tail wagging the dog. And how can that be? The field in the corona is pretty much formed by what's in the photosphere. We make extrapolations upward into the corona and try to explain and understand what the field is like up there. And as you point out, essentially it's the photosphere which is forming or producing what the field is. But with one exception, though. Because there are stresses in the magnetic field, currents can form. And as I'm sure you know, the currents make the field, in some cases, different from what you would be able to extrapolate upward from the photosphere alone. It's possible to have closed current systems in the corona, and without an obvious connection or an ambiguous connection at best to the photosphere. So the photosphere observations, particularly just the line of sight alone, are not enough to constrain what the coronal magnetic field is, or the flare is presumed to form. So you can have many configurations of the coronal magnetic field that all match the photospheric field. And it's a matter of energy that gets stored in the corona to make the flare and release it. And you could have the case where a lot of energy gets released in the corona and almost nothing happens in the photosphere. But that isn't what we see. And I can't answer your question completely because, as I pointed out, most of the observations we have to date are consistent with the idea that the field lines are mainly horizontal and pop up to explain these changes that we see. But not all of them. How can we explain a polarity reversal near this center? It's as if a field like this is going down, and that's a little hard to understand. The notion right now is that there's essentially a collapse of the field lines. I can't draw it in my... We'll try it this way. Photosphere. Field line comes up, forms an X-type neutral line, and a reconnection occurs here. There are connecting field lines there, below it, connecting two opposite polarities. That system collapses as material is thrown up outward above the reconnection point, and material comes downward below the reconnection point. That tends to pull up the field lines on the periphery of that. It's a very bad picture. It's all we've got right now, though. And once we get the vector observations that show in detail how those field lines are changing, that'll restrict the ambiguity that we have right now quite a bit. And then I think we'll get a clean picture of what's going on.
May I make a comment? It's about this part on the quasi-some magnetic fields. Mm-hmm. You put this dividing line in 2006, I guess with the first light of Solis, dividing what was known before and after. I would put a very, mark divided line 6 years before. It's about year 2000 or so. There is this paper, this numerical simulation by Fausto Cattaneo of a turbine dynamo, showing showing magnetic fields that have all kinds of field strengths, tend to be concentrated in downwards. They emerge as horizontal features in the granules. They show mixed polarities at the resolution that they should show up. And in 2002, we did this work with Bruce Lights of a misma inversion of quite some profiles. We basically show all these features. Mixed polarities, strong and weak fields all together, the possibility for the fields to be highly inclined. So, things were changing a little bit before 2006.
Yes, I knew I would get into trouble here.
So, it's a beautiful talk, by the way.
No, I appreciate what you're saying completely. And to get myself out of this trap, what I'm going to say is that what I was referring to is the rapidly changing horizontal component of the field, not just the existence of horizontal fields and magnetic fields everywhere. And I agree with you that around the beginning of the 2000s, there was a lot of nice work going on showing that, and again, some of it being done right here. And there's a lot of history in the study of the inner network fields that I did not cover, and I apologize to those of you who did that work, but I had to stop at some point. In fact, I'm glad I stopped when I did.
So more questions, Arturo? I just want to say that I've been looking to Fausto's simulation, dynamo simulation, and there's no flux emergence there with horizontal fields. And indeed, Fausto has explained to me why it doesn't happen in this simulation. So, we can enter into a long discussion.
Well, yeah, Fausto gave a nice talk at our place and stimulated a lot of this work. Yeah. So Fausto is much more dynamic than I am. I'm just an observer.
So talking about dynamics, I was very happy you just said that what do you see with these teeth in horizontal magnetic fields, with these teeth in the fields, is the dynamics of this horizontal component. Mm-hmm. That makes me a lot of pleasure, But that prompts a question, isn't it, that why the horizontal component will move so dynamically while the vertical seems to be happier with its own particular state?
You want me to answer that?
I don't know. I want to comment.
I'll try.
I don't have any answer.
Well, all I can say is that looking at the MHD models, the radiative MHD models, it shows the horizontal component changing much more rapidly than the vertical component. Well, that's a cop-out. That doesn't say anything about the physics except what's built into the models. My picture of it is that as granules are driving this changing magnetic field, the driving by granules is more powerful on the horizontal component than it is on the vertical component. The vertical component sits there and more or less passively moves around in response to the granules pushing it or sucking it into different places. But it doesn't seem to tear it apart as much as the horizontal component is getting bounced around. That's not a very good answer either, but
good enough.
That's my picture of it.
I can make a comment. The first time we have seen the evolution of this horizontal component is with the IMAX magnetogram. So we haven't published that yet, but I have the same question as you. Why is so fast at the limb and the horizontal? Yes. I mean, it's really fast. We'll see. I think we need...
Well, the motions are basically up, down, in the granulation.
Okay, so more questions, and I will not make any comment. I have one question, though. Fernando, okay. You could have told me.
So, like Jorge was a bit puzzled about the first part of the lecture, the observations of photospheric fields when a flare goes off. And so I was wondering, an important fraction of the flares are observed to occur after flux emergence has taken place in the photosphere. So that seems to be at variance with your results. If there is flux emergence, then you should see some changes in the photospheric field before the flare goes off. So maybe you want to comment?
Yes. On May 21st, 1980, there was such an event that I studied in some detail. And it was a fairly large flare. And indeed, it was very obvious that it looked like the trigger of the flare was the eruption of a slightly opposite polarity feature within the existing active region. So no doubt things like that occur. We haven't actually looked specifically at the longer time history of the active region evolution to see if many of these features we've observed are in fact related to flux popping up and causing some reconnection with the existing flux. But I have no doubt that such things exist, and some fraction of the features we've looked at are probably related to that kind of a phenomenon.
So, Hector, okay.
So if you look at the large project that the solar community is involved with right now, it would appear that the interesting chromospheric magnetism is now geared towards very high resolution, relatively small fields of view. I mean, SOLIS seems to go in the orthogonal direction, trying to look at the full disk, moderate resolution. Is this because this is just the window of opportunity where you can separate yourself from what everybody else is doing, or do you really think it's more interesting to look at the sun as a full system instead of focusing on bits and pieces and look at them in very high detail?
My answer is yes and yes. To the first point, when the SOHO satellite was launched and MDI started producing nice magnetograms from space, we said, oh, we've got a problem here. How can we compete? said, aha, we can look at the chromosphere. So we started making observations then. And it was driven basically by nothing more than that, although there was some underlying curiosity because we'd made chromospheric measurements well before that, 20 years earlier, and they were interesting. But nothing specific had been done much with them. So the initial motivation was, ooh, we got to be competitive. But like often happens in such situations, you find things that are interesting. And then the knowledge that you might gain about the sun becomes the main driver. And when we designed SOLAS, we said, well, of course we have to have a chromospheric capability because it's an interesting area of the sun's atmosphere, needs to be studied. Nobody else is studying it on a regular basis. Let's do it. And we're sure to find some interesting things. And I hope I conveyed to at least some of you that we are finding some interesting things in the chromosphere because of these relatively low resolution, not space-based observations. You could still do some good stuff on the ground. We can't compete in terms of resolution, and that high resolution work needs to be done for sure. We've got to understand in detail what's happening. A lot of our low resolution measurements may be contaminated by bad analysis, assumptions of the nature of the field across a pixel that are not correct or justified. So we've got to have the high resolution to quantify and justify making low resolution observations that are worth anything. Maybe all this stuff is fantasy when we get enough resolution to see exactly what's going on. But I like the large scale picture of things. I always have. And so that's one of my weaknesses.
I would disagree with you, Hector, too. I think we haven't seen the chromospheric magnetic field nor at a smaller scale, high resolution, neither at larger scale. So we know pretty much nothing. I mean, a few things. So everything is welcome. Indeed, I would say vector solid, not just longitudinal solid is what we need. So that's my opinion. Okay. So if there are no more questions, I'll put mine, which is very earlier in your talk, you said that flares are the most energetic phenomenon that happens until 2 light years. So what happens at 2.1 light years that is more energetic than a solar flare?
Well, I put that in last night thinking, how far out can we go and say that flares are the most powerful explosions? I said, well, let's see. I vaguely remember that Proxima Centauri was a flare star. I said, better not go more than about 2 light years. So that's all.
Okay, good. So,
but my internet connection was down, so I couldn't check.
Yeah, Google didn't help them. Jack is here until tomorrow, and I know Jorge wants to speak with him. Christoph wants to speak with him. If you want to speak with him, just let me know. And then he'll be giving a talk at the University of La Laguna. It's not for students, but some of you may be welcome there, at 12:15 tomorrow at the physics faculty. Okay. So, coffee break in the cafeteria at 12. Okay. So let's thank Jack again for.
Thank you all so much.
I think as